So this is a graphical representation of f of k. I have k on the x-axis and y, which is output on the y-axis. So f of k has the properties we have described earlier. So it first of all, the in-ADA conditions are respected because at 0, then there is no production. So if 0 capital, no production. And then capital has decreasing returns, meaning that the more I accumulate capital, then the less each extra unit of capital helps me produce output. Now, we could imagine that if this goes on forever, then at some point at some infinite amount of capital, then the marginal productivity is actually 0. So now the question is, so we want to represent savings. So this is the total production of the economy as function of its capital stock. Now, what we're saving, if we remember, they are just a constant fraction of the total output. So this means that basically we should see about this same shape here, but just a fraction of it. So, but it should have the same, exact same shape. And this is what it looks like. So it's just s, a fraction of s. Here it looks like it's maybe 20%. Multiplied by f of k. So sf of k, or investment as function of capital, has the same shape as production as function of capital. All right, so now what we have to show is depreciation. So before I show you the answer, so just think in your head what kind of shape should the depreciation as function of capital look like. All right, that's enough. So as we can remember, we had a constant fraction of capital that was depreciated. So it means that it should be just proportional to the amount of capital. So it should be straight. And that is what we show here. So of course, if I have 0 capital, I have 0 depreciation. And if I have much capital, then I have more depreciation. So then that's about it. That's the basic model. Now the question is, where is that going to go? So here there's no time, there's nothing, but we can still imagine what the dynamics should be. If we want, what we can assume is let's imagine an economy that starts with some amount of capital. Let's say this quantity here. And then we can ask ourselves, where is this economy going in the long run? So is this economy going to accumulate more capital or lose capital? So how should we look at that? Well, we have to compare investment and capital loss or depreciation and see if one is bigger than the other. So at this quantity of capital, what can we see? Well, we see that investment is S times f of k, so it's here, and depreciation is delta times k, so it's here. So what do I see? I see that investment is bigger than depreciation, so it looks like capital stock should grow. And actually, if we were in discrete time, then all we could see is if I'm here this year, then, or if t is some year, for instance, then I can just measure the difference in height between the two curves. And this gives me exactly the amount of capital I get next period. So I would get something like this amount here. So I would move from here to here. So and then I can start again asking myself, where am I going? So I see that still investment is larger than depreciation, although I see that since depreciation always increases at the same rate, whereas investment peters out as capital increases, then the gap is becoming smaller and smaller and smaller. But still, as I'm still on that side of the graph, then it looks like I should always get a positive growth rate of capital. Until where? Until I get to exactly this this point here, which looks like somewhere that is stable. Because why can I see this stable? Well, because depreciation is exactly the same as investment. So here I'm in a steady state, basically. My economy doesn't change. Now I can do the same thing on the other side and ask myself, am I growing or am I decreasing in capital stock? Well, I see that here it looks like I have too much capital compared to the amount of investment people are willing to make, because the depreciation is here and investment is here. So the net growth of capital is negative. And by the same logic, I'm going to slowly but surely head up in the same direction to this point there. So this point there looks like in the long run where we always are going to end if we start with some positive value of capital. So let's indicate that quantity with K star, and so we're going to name this quantity the steady state quantity of capital for this economy. And you see, of course, that it is a function of the shape of f, it is a function of delta, it is a function of s. So if I change some of these parameters, then of course this steady state will change. So all right, can we see other things on the graph? Well, yes, because when I have K star, I can, since I know everything else, I know the size of my economy, I know investment, then I can deduce everything about everything that's going on at the in the steady state, because as we said, K is a state variable. So then what can I know? Well, I know that total production is going to be here, f of K star. Total investment is going to be here, SF of K star, and total depreciation is going to be the same value, delta K star. And what is going to be consumption here? Think about it. What is consumption? Consumption is whatever is left after I invested some amount, or in reverse, it's what I take before I leave something to invest. So it is this quantity here, f of k minus sf of k. So I can indicate all of these quantities here. So y star is this, I star is here, so investment, steady state investment, and steady state consumption. Okay, so did I tell you everything about what there is to know about this model? Especially about the steady state. So one thing that is going to become very clear soon enough is that every time you have this kind of graph, then most of the things that are interesting happens at when lines cross. So if you're at the exam and you're totally confused and you don't know what you have to find, then look on your graph. If you see some lines that cross, then probably there's something interesting there. So, and that's where we have the steady state stock of capital. But is that the only place where the two lines cross? Well, no, they also cross here. They also cross at 0. What's happening at 0? Well, I have no capital, so I don't produce anything, as said by the INADA conditions. And also, I don't have any depreciation, so my stock of capital cannot depreciate more than 0, since I cannot have a negative amount. So if I'm stuck here, then I don't move. It's also a steady state. But of course, it's not an interesting steady state. We don't really... No country has 0 amount of capital. So one assumption we make usually is that we start with some positive stock of capital when we analyze the Solow Swan model. All right. So that's most of what we have to say about the dynamic. Now, just one question before we end. So during 1950s, 1960s, why did West Germany and Japan grow at 6.6% and 6.8% respectively, while the US only grew at 1.2%? You can pause the video and think about it. All right, so what's fun to have a live class is that we get very good suggestions, and since it's historical questions, many things may be true. Here are a few suggestions. So what happened, especially in Germany and Japan, just before that period? Well, if you know one or two things about history in the 20th century, then you know that these countries were almost entirely destroyed after the war. So they had very little capital. Of course, they had also their population decreased quite a bit, but still we can imagine that the stock of capital really decreased. So what would have happened? Well, K is, imagine they were at steady state, then K would have moved, say, here. And then what happens here? Well, K increases really quickly. Whereas in the US, there was almost no destruction, or no destruction during the, except at Pearl Harbor. So they were almost at probably close to steady state. So then, as we're going to see later, other factors are going to explain US growth, but it was nowhere near the growth of West Germany and Japan. Other things were going on. So there was the Marshall Plan and then the Mutual Defense Plan that followed it in West Germany. And similarly, the US helped a lot Japan. So that's outside this model, because here we assume that it's a self-contained economy, but here we had huge amount of foreign investment to help West Germany and Japan grow again. So they had capital coming from outside, which is totally not explained within this model endogenously, but still that's something we have to keep in mind. All right, so we're almost done. Now we're going to just formalize the INADA conditions and have some quiz. Oh yeah, one last thing is, why do we need the INADA conditions? Well, we need the INADA conditions, first of all, because we absolutely want this investment curve to be above the depreciation curve for a small amount of capital. So if the slope here is infinite, that's this makes sure that this is happening, because delta is not infinite. And then since SF of k is going to be flat at infinity and delta k is always increasing, then we're sure that there's a single crossing here. So a single existence of the equilibrium. So that's why we need the INADA conditions.